Hi, in this class we will present the array partitioning optimization, which allows to optimize the usage of RAM resources in order to improve the performance of the kernel. As we have seen in the previous classes, by using both loop pipelining and loop unrolling, we can achieve very interesting results. In particular, coming back to our vector sum example, we have seen that within an unrolling factor of 2, we managed to almost reduce the loop latency by a factor of 2, compared to the implementation in which we only used loop pipelining. Indeed, with an unrolling factor of 2, the loop performs 2 computations in parallel at every iteration, and such computations are also pipelined with an initiation interval of 1 clock cycle. So far so good, but when we tried to improve performance further with an unrolling factor of 4, we got the same performance. Indeed, while we have the trip count, we also doubled the initiation interval. Furthermore, even if it has a small impact, the iteration latency has also increased by 1 clock cycle. The issue comes from the number of memory ports available for reading and writing data to our local arrays, local res, local A, and local B. Indeed, by default, each local array gets mapped to a local memory on the FPGA that features up to 2 memory ports for read and write operations. Alright, so how can we overcome this limitation? Well, we have just said that each array gets mapped to its own local memory on the FPGA. So why not using multiple arrays to increase the overall number of memory ports? Sounds like a solution. Let's see how we can achieve it by modifying our code. First of all, in order to better visualize the issue, it helps to manually unroll the loop instead of using the HLS unroll pragma. This code is equivalent to the previous one, except we did the unrolling manually. As you can see, for each of the 3 arrays local res, local A, and local B, we have 4 different elements to access. In particular, we need to access the element at position I plus 1, I plus 2, and I plus 3. Since the local memories only feature 2 ports, it means that we can only access the elements at position I and I plus 1 in 1 clock cycle, and access I plus 2 and I plus 3 in the next cycle. It is also important to note that the value of I increases with a step of 4 in every iteration. Hence, the elements that we need to access change from iteration to iteration. Here we have a picture of which elements of array local A are accessed over the iteration of our unrolled loop. In order to be able to achieve an initiation interval of 1 clock cycle, we need a way to access element 1, 2, 3, and 4 in parallel, as well as elements 5, 6, 7, and 8 in parallel, and so on. To achieve this, we can apply the array partitioning technique. The overall idea is to reorganize the data of the original array into 2 or more smaller arrays, or better partitions, so that each partition is mapped to its own memory with its corresponding read-write ports. The key aspect here is to decide how to reorganize the data. In our example, the best solution is to perform the so-called cyclic partitioning. In particular, here we perform cyclic partitioning with a factor of 4, meaning that we create 4 partitions from the original array. With cyclic partitioning, the data from the original array is spread out to the partition in a cyclic fashion. The first element is mapped to the first partition. The second element is mapped to the second partition. The third element is mapped to the third partition. And guess what? The fourth element is mapped to the fourth partition. Then the cycle repeats. The fifth element is mapped to the first partition. The sixth element is mapped to the second partition, and so on. We named our partition as local A0, local A1, local A2, and local A3. This picture shows the actual data stored in each partition. As an example, the partition local A2 stores at position 2 the element at position 10 from the original array. Alright, now it's time to rewrite our code by using the 4 new partitions instead of the original array. As you can see from the code, all the accesses to the original arrays at addresses I have been substituted with accesses to the first partitions. The accesses to I plus 1 have been substituted by accesses to the second partition, and so on. Notice also that when accessing the elements within the partitions, we also need to divide by 4 the value of variable I. Indeed, each partition only contains 1/4 of the elements of the original array. Alright, so far so good, but we are not quite done. We modified the code that performs the actual vector sum. But what about the code that takes care of reading and writing the data to and from the local arrays? We also need to ensure that the data coming from the external DDR gets properly stored in the way we intended. And similarly, we need to send back the data in the same order we had before partitioning the array. First of all, we define all our partitions. As an example, instead of declaring the array local A with n elements, we declared 4 arrays, local A0, local A1, local A2, and local A3, each of n divided by 4 elements. Then, we need to change the logic for reading the data from the DDR memory. Instead of using a simple memcopy, here we manually write a pipeline loop that at each iteration reads one value from the external DDR and stores it in the correct partition of our local array. In this code, we use the modulo operator, the percentage symbol, in order to understand the correct partition to use for the element at address I of the original array. In practice, when using cyclic partitioning with the factor f, the element at address I from the original array is stored in partition number I modulo f at address I divided by 4. Notice that here we mean integer division. The result of an integer division is simply the result of division without the fractional part. Once we have read the data, we can now perform the computation using our vector sum loop as shown before. Finally, we also need to send back the results. To do so, we need to collect the data from the partitions of local res and send them to the external DDR. The logic is similar to the one we use for reading the data from the DDR. We create a pipeline loop, and at each iteration, we fetch the correct value from one of the partitions, and finally, we write the value to the external DDR. Again, we use the modulo and the integer division operations to retrieve the correct value from the partitions. Alright, we did quite a lot of work. Let's now see if it was worthy by running Vivado HLS synthesis. Awesome! We managed to get an initiation interval of 1 clock cycle and the latency of the vector sum loop almost halved. Thanks to our partitioning scheme, every iteration of the loop accesses exactly one element from every partition, which has its own memory port. Overall, we can perform all the read-write operations in parallel, and we are able to achieve the ideal initiation interval of 1 clock cycle. Okay, it worked, but is there a simple way to achieve the same results without the need to rewrite such a large amount of code? Likely enough, the answer is yes. Vivado HLS provides the array partitioning pragma for this purpose.